Okay, so in this third video, we're going to go over some of the basic equilibrium calculations. So what we're going to do is we're going to calculate an equilibrium constant. We're going to calculate values of equilibrium concentrations for a reaction using an equilibrium constant. So we're going to start off with a new reaction here. We're going to start with the reaction forming hydroiodic acid, or HI gas, from hydrogen and oxygen. We'll start off fairly basic, and we'll just write the equilibrium expression. So what I want you to do, pause the video, take about 30 seconds or so, write the equilibrium expression for this reaction. Okay, so what we should have for an equilibrium expression. So our equilibrium expression is going to be K. I'm actually going to do Kc or Keq here because I don't want to do much in the way of Kp just yet. So Keq, remember, is products over reactants. So product is going to be Hi raised to the second power because we have this 2 coefficient divided by concentration of hydrogen gas times the concentration of iodine gas. Right, so this is our Keq expression for this reaction. So our second question is going to take this expression, and now we want to actually calculate the equilibrium constant. In this case, I gave you the concentrations of everything at equilibrium, and from this, we need to calculate our equilibrium value, or K. It won't always be this straightforward, but we're going to start off fairly easy with this one. Right, so what I want you guys to do is take the equilibrium expression you had in the last reaction, pause the video, take about a minute, plug it in, calculate the value of Keq. Okay, so if you were able to get this, congratulations. We'll actually take our expression, right? So Keq is equal to Hi squared over H2 times I2. So concentration of Hi is 1.87 times 10 to the minus third. And we are going to square this over 6.5 times 10 to the minus fifth times 1.065 times 10 to the minus third. And to 3 significant digits, or actually, sorry, we should technically only use 2 here because we have 2 digits here, 6.5. We wind up with an equilibrium constant that is approximately 51. Right, so if you were able to get 51, congratulations. If not, just take a little moment, go back through the problem, and see if you actually can grab that now. So our third problem is going to be calculating equilibrium concentrations. Right, so here, I give you the initial concentrations of the mixture. So I said that H2 and I2 are each 2 times 10 to the minus third molar. Now we have no Hi to begin with, so when the reaction eventually hits equilibrium, I want to know what the concentration is going to be of all 3 things in the reaction. Now what we have to do is, again, we have to figure out, we know what they are at the start, but we need to figure out what they are at equilibrium. To do this, we're going to use an ICE table. For those of you who have ever seen the BCA method or before change after method of doing stoichiometry, it works much the same way. ICE tables are dead easy to work with. Right, so we'll actually show you an example of an ICE table on the next slide. Right, so an ICE table, the way it's going to work is we start off by writing our reaction. Right, so we're going to have H2 plus I2 yields 2Hi. So I is going to be initial, C is change, and E is equilibrium. Right, so ICE. And we're just going to make a table of these values at each place. Right, so our initial value for H2 and I2 were each, I'm not going to leave the decimal points in, 2 times 10 to the minus third and 2 times 10 to the minus third. Now, because the reaction hasn't actually done anything yet, we don't have any product, so initial concentration of HI is 0. The change column works by using the basic rules of stoichiometry. Right, so whatever this change is here for H2, the change for HI has to be twice that much because the coefficient's twice as big. Now the thing is, we don't know what the change is, do we? If we don't know, we're just going to use a variable. So I'm going to call it X. Now we're going to lose some amount of hydrogen, right? The reaction is going to go in the forward direction because right now that's the only direction it can go in. So we're going to lose some amount of X. Similarly, I2, it's a 1-to-1 ratio. We're going to lose the same amount here, so we're going to lose X from I2. And for HI, we're going to gain twice as much, so we're going to gain 2X. So our equilibrium values are going to be 2 times 10 to the minus third minus X. 2 times 10 to the minus third minus X. And 2X. So this is our completed ice table. Right, so we have our ice table, and now what we're going to do is we're going to take our equilibrium expression. We say KEQ is the concentration of HI squared over the concentration of H2 and I2. Now, another thing to keep in mind with this, yes, we're going to put the 2x in here, and then we're going to square it. So for equilibrium values, this 2 actually gets taken into account twice. It gets taken into account in the stoichiometry step for the change, and by squaring it here. Right, so from here, all I have to do is I'm just going to plug in some numbers. Right, so our KEQ we figured out was 50.5 equals concentration of HI squared. So that's going to be, and I'm just going to say 2x quantity squared over. Now these are both the same, and since we're multiplying them by each other, I'm just going to do 2 times 10 to the minus third minus x quantity squared, because I'm just multiplying two of them together. And then all we do is we go through and solve for x. Now notice here, this is actually a very straightforward solve. Right? The reason why it's a straightforward solve is because since this side is entirely a perfect square, all I have to do to solve this equation is just square root both sides. Right? So I'm going to get 2x over 2 times 10 to the minus third minus x is equal to the square root of 50.5. From here, you can go through, so take a couple minutes, go through, actually solve for the value of x, and we'll see what you get in a moment. Okay, so when I went through and did this, I got a value of x equal to, I'm going to say 1.6 times 10 to the minus third molar. All right, so 1.6 times 10 to the minus third is going to be our concentration. If you're plus or minus 1 here, that's perfectly fine. Because I used 50.5 instead of 51 on the previous slide, so sig figs, again, you may be a little bit different. Right, so that's solving for x. Now all we have to do is we just have to put it back together. So this right here is how you use an ice table. So now we'll put it all together with that 1.6 times 10 to the minus third. Right, so for our solution, from our ice table, we know the following. We know that the concentration of hydrogen at equilibrium is, I'm actually just going to do it in 0.002 minus x. Right, so that's 2 times 10 to the minus third, obviously. I2 is the same. And HI is equal to 2 times x. Right, so we plug in our value of x from our previous slide, and we wind up with 4.4 times 10 to the minus fourth for each of these two. And here we wind up with 3.1 times 10, oh sorry, not 3.1, 3.2 times 10 to the minus third for this. Right, so these are our three solutions for the problem that occurred. Right, so concentration of hydrogen at equilibrium, concentration of iodine at equilibrium, concentration of HI at equilibrium. Right, so this is actually working with equilibrium constants and doing the math and using ICE tables. Now, a few things to keep in mind when you're working with an ICE table. So some helpful hints. Most major helpful hint. If the value of K is ridiculously small compared to the concentrations you're given, then that whole minus X term we can ignore. The reason why is because if K is really tiny, X is going to be extremely small. Right? And if X is so small that it's not going to affect the sig figs that we're working with, you don't even need to include it. Now, with that said, what you want to do is go back and check once you've solved. So if your X value winds up being about 5% of your initial concentration, actually go in and plug the minus X term into your expression and recalculate. Please note, you cannot ignore an X if you're adding it to 0. Right? Because 0 plus some very small number is a very small number that exists. A very large number minus a very small number is still just that very large number. Right? So that's one thing to keep in mind. This is a great way to shortcut questions. The other thing to keep in mind is that for the AP exam, you will not be asked to use the quadratic equation. So on an AP exam, all of your equilibrium problems will either be straight linear or perfect square. So you can just solve them using that. Now, for stuff we're going to work with in class, I'm not going to make that same guarantee. You may have to use the quadratic formula in class. If you have it on your calculator, that's great. Just one thing to keep in mind is make sure you take whichever root gives you positive values at the end. Right? Because especially if you mess up your x's, so for example, if your product wasn't 0, if your product was a number, and you plug in minus x and plus x, let's say you plug them in on the wrong side, so what you thought was a minus x should have actually been a plus. In that case, your negative root will actually work as the solution. So just keep in mind whichever one overall gives you the positive end value is the one you want to use.